All right. Thank you, Marty, for kicking us off today. And also, I should say, for your leadership along with Brad Murray in setting up the Discipline 101 seminars that are taking place this semester and will continue throughout the duration of the Seacoast RCN. So I'm glad to be here today and to be partnering with Brad Murray to share some of the basic principles and the dynamics that underpin research in coastal geomorphology. And because I know we have a very broad range of disciplines represented here, I thought I would start by answering the question, what is geomorphology? Broadly defined, geomorphology is the study of landforms and the processes that create and reshape landforms over time. And so in coastal geomorphology, we're really focused on landforms and processes that operate in coastal environments. Let's see. So to give you a sense of where we're headed, as Marty mentioned, there are two parts to this with Q&A following each part. And what we're looking to talk about here and in part are the causes behind coastal shoreline erosion and the factors that determine how storms impact sandy beaches and barrier islands or barrier spits and mainland barriers also apply here. We also talk about the processes that maintain barriers and allow them to persist over time as conditions change. And we will talk about the role of sea level rise and changes in the frequency of intense storms in maintaining these landscapes. And then we'll also be talking about and presenting some of the really important interactions and feedbacks between the natural processes that we'll be sharing with you and coastal management decisions that take place in these environments. So what we're going to talk about here today relates to any sandy, low-lying, open ocean environment. And the North Carolina coast is a beautiful example. In plan view, of course, we can see the barriers, bays, and marshes that are typical of such a coastline. And we could also consider this landscape in cross-section, which is shown schematically here on the right, where the near shore gives way to the beach and the dune environment, and in developed coastlines, of course, we have homes and businesses and infrastructure located on the barrier itself, and then behind the marsh and the bay landscape. We've split our presentation into two parts, such that I'll focus on the processes that have to do with storm impacts and sea level rise, which can best be depicted in the cross-shore profile. And then Brad will pick up for part two, and he's going to focus on coastline position and shape, and changes in coastline position and shape that are best described in the, or depicted in the plan view. So what we're gonna focus on really will be the barrier island landscape in our talk today, but most of the points that we'll make and most of the dynamics that we will talk about will really apply on any low-lying sandy coastline. All right, so the effects of storms. Well, the primary effect of storms on coastal processes and low-lying coastal landforms is through the impacts of storm surge. And storm surge, I mean, we're probably all, we've heard this term regardless of our discipline, right? Because storms have severe impacts in coastal areas, and there have been a number of storms over just the last few years. And so in the news cycle, we're hearing about these processes. But storm surge is produced predominantly by the winds associated with storms, which push water toward shore. And the stronger the winds, the larger the storm, the more water that's pushed landward. And low-lying landscapes are especially vulnerable, and storm surge is especially pronounced on low-lying landscapes because they are associated with shallow, low-sloping offshore environments, which means there's really nowhere for that water that's pushed landward to go other than upward. And so added to this is the effect of large waves that are generated by storms, which further elevate the water level, both because breaking waves push water landward, and and elevate the water level in that way. And also because larger waves run up higher on the landscape. And so we have these two components of wave setup and wave run up, which are added to storm surge that cause total water level during storms to be much higher than even the highest tides that occur during non-storm conditions. So if we think then about the effects of storm surge and water level elevation due to wave impacts on beaches, it's really the relationship between this total water level and the elevation of the landscape. So the elevation of the beach, the back beach, and the dune, or the island, if we're thinking about Barrier Island landscape, that determines the impact of storms. And some of you may be familiar with really seminal paper by Salinger 2000, which casts this in several different categories. And so first we could think about when the total water level during a storm is lower than the height of dunes. And here showing on the left a post-storm beach where we have the dune line, which is pretty low dune associated with houses right behind it, and a beach pre-storm. And then post-storm, we see that sand has been moved offshore. And in this case, the effects of the storm are pretty much confined to the beach and the dune environment. And so sand is moved offshore, and fair weather waves following storm conditions will tend to move that sand back onshore during non-storm conditions. And we could look at this in cross-section and say that, you know, moderate storms cause a cycle of shoreline change. And for those who don't study geomorphology but are familiar with coastal environments, you will recognize this as you observe beaches over time, that we have this shoreline position where the water meets the land under normal conditions, which is moved landward as sand is moved offshore during storms. And then following storms over time, the fair weather waves bring that sand back onshore and the shoreline moves seaward again. And so this is a typical storm recovery cycle that we see over time in coastal environments. Now we can consider the effect of a more intense storm, in this case where total water level where the total water level is above the height of dunes. And in this case, overwash occurs. And so here showing a picture of Route 12 following Superstorm Sandy. We have telephone poles and a truck for scale. This line that looks so small across the middle is Highway 12. And this is a large overwash fan that was generated by storm surge and wave action during Superstorm Sandy. And in this case, sand is moved from the beach and dune environment onshore and placed on top of the island interior. And overwash deposition in this way actually increases the elevation of the landscape, which turns out to be really important, and we'll come back to that shortly. Now, this is a natural system here, essentially, in that there is no development except for a road. We could look at this process when it's superimposed on a developed landscape. And on the left here, Oak Island, a recent image showing, again, overwash exceeding the dune height and the height of the back beach, and we get sand being moved onshore, and here overwash deposited on roads and driveways and properties. Another picture here from Superstorm Sandy, now in New Jersey. Again, more damage in this picture, but overwash deposition taking place. So in the case of development, overwash deposition also increases the elevation of the landscape, but I have a maybe here. Because there are some effects of development on this process that we'll come back to in just a bit. So we could also think about the effect of extreme storms. And these would be storms where the total water level far exceeds the height of the landscape. And in this case, the landscape becomes completely inundated, and an island will essentially become part of the ocean during the storm. These are where those extreme stories of folks who have not been able to evacuate but ended up being unluckily right in the location where storm surge is worse and find themselves really in kind of ocean conditions, even within their own neighborhood. And here, just looking at a natural environment, the Chandeleur Islands off the coast of Louisiana, pre-Hurricane Katrina and post-Hurricane Ike, and both during Katrina and during Ike, the Chandeleur Islands were completely submerged and purely inundated. And you can see that you really don't see much sand here at this point. And so sand here, in this case, is moved not only on top of the island, it's moved beyond the island. And so we don't see much sand even left behind. So this is an extreme case where sand is actually lost from the island system to the bay behind. And we could think about what this looks like in the midst of development as well. On the left, this is Bolivar, Texas, after Hurricane Ike in 2008, and Holly Beach, even after recent Hurricane Laura in 2020. And you know, Hurricane Ike produced storm surge here of almost 19 feet. So that's about equivalent to a 2-story home. And this is a pretty famous house called the Last House Standing. This is a picture taken in the waning stages of Hurricane Ike after it had passed. In this case, inundation persisted for a while because there was so much water piled on that it took a while for it to drain. You know, this is the ocean side, this is the bay side, and you can see that during the storm, they were fully connected. So there you can see a little bit of remnant of homes here, but this is a community that was fully developed. Same in Holly Beach, we're not seeing a lot of deposition here, right? The sand is lost to the bay system behind. So the processes that occur during moderate storms, when we see overwash deposition on islands, is really important. And barriers actually exist and persist through time because of overwash deposition. Overwash deposition during intense storms is what has maintained islands over time. Barriers, you could think of them essentially as piles of sand that have been created during storms. And storms can only reach so high on the landscape, and how high they can reach to deposit sediment on the landform will determine how high a barrier tends to be. There's an equilibrium that gets established there between the total water level established or that tends to be achieved during storms and the height of the barrier landform. And once overwash deposition has built up that landscape above sea level, or when it maintains it above sea level, in between storms, there are other processes that serve to build up island elevation even further. So in between storms, dunes, which are formed due to wind processes or aeolian processes that transfer sediment across the beach and blow them into the back beach, and cause interactions with vegetation, which actually slows the wind, causes deposition. You could think of vegetation as trapping sand, cause these dune features to build over time. And by elevating the surface of the island, actually provide protection for communities, both human and other habitats, by reducing vulnerability to overwash and inundation. A real key here is that for dunes to form, there actually needs to be enough time in between storms for these wind and aeolian processes to take place, and for this, we call it a dune building feedback, to kick in, where the interactions between the wind transported sand and vegetation allow that topography to grow. So dunes will tend to recover and reform following storms if there's enough time for them to form, if there's enough, if there's a location for them to form in. But there is the possibility that if storms occur too frequently, then dune recovery is hampered, because storms will reset the dune building process if dunes haven't reached an elevation that's above the total water level that a storm produces. So we could think about now, you know, everything I just said really has to do with storms, kind of thinking about static conditions, but what about under conditions of sea level rise? And I'll just say here, you know, as a geoscientist, I think about shorelines are not static. So 18,000 years ago, there were many glaciers. Glaciers covered much of the landscape. Water was trapped in glaciers. Sea level was much lower. So sea level has actually been rising for the last 18,000 years. The rate of sea level rise slowed about 6,000 years ago or so. And this is when barriers started to come into existence, formed through those storm processes that I just described. So sea level has been rising for a long time, but of course what we know about the future is that sea level rise rates are expected to increase, and increase rather rapidly. So what about the effects of sea level rise on the processes that I just described? Well, sea level rise basically means that the total water level achieved during storms will be even higher than it has been historically. And an increase in total water level leads to the increases in the frequency or the likelihood really of overwash and inundation. So we'd expect to see more impacts in this realm in the future due to the same storms that we see now will be more impactful in the future due to higher water levels as sea level rise occurs. And then there's also an expectation that we'll see an increase in the frequency of major hurricanes in the future. So these would be hurricanes category 3 through 5. And of course, the bigger the storm, the higher the storm surge is likely to be. And if we have higher storm surges that are more often, this will again tend to increase the frequency and the likelihood of overwash and inundation occurring during storms. So more frequent overwash as sea level rises, and if storms become more frequent, will tend to maintain island elevation relative to sea level, because it is the storms that are depositing sediment on top of islands and building island elevation, allowing dunes to form above that elevation. And in removing sand from the beach and the dune, overwash actually results in shoreline erosion. So when we talk about shoreline erosion, there are several factors that cause it to occur, but the removal of sand from the beach and the dune through overwash is one process by which a shoreline is moved landward as islands maintain elevation relative to sea level. Now, overwash also maintains island width. So not only island elevation, but island width. And well, how does this work? Well, we could think here about shoreline erosion, a nice image from the National Park Service here, showing that overwash occurs in this environment, and you could look and see the edge of the former back barrier here, right? And overwash in this case is actually extended beyond the back barrier. And so in this case, where it's possible for overwash to extend not only across the island to build elevation, but also behind the island, we're seeing a back barrier extension. We're seeing growth or landward movement of the back barrier shoreline as well. And in this case, we're not just narrowing the landscape through erosion, we're also widening the back barrier, maintaining width. And that means that the island form itself is able to migrate landward as sea level rises and overwash becomes more frequent. And this is in contrast to a situation where perhaps overwash deposition can't occur. I'll talk more about this in a moment, but in this case here in Buxton, North Carolina, there is a road and that road needs to be maintained. And so understandably high dunes are placed in front of the road. And so when overwash occurs during storms, in this case, it's not able to be transported. If it does make it onto the road, it's bulldozed back into the dunes. And so here we're not actually seeing the possibility in this circumstance for maintenance of the width of the island. Instead, the island gets narrower over time. And there are implications for this that I'll come to in a moment. So the processes that I've been talking about that take place on barrier islands around the world, and they have taken place for the last several thousand years because, as I mentioned, sea level has been rising over this time. And as rates of sea level rise increase in the future, we can expect these processes that generate overwash and shoreline erosion resulting from overwash and island migration to become even more dominant. And it's important here from the perspective of geomorphology, and what a geomorphologist sees is that in order for islands to persist in the face of rising sea level, these overwash processes need to take place in order to maintain the elevation and the width of islands. It turns out that many of the actions that are undertaken in coastal environments, understandably, prevent or undo overwash deposition. And we're learning more about this all the time. But in the case of even a soft, what we might call a soft approach to coastal management, where we build and help that dune building process along by reconstructing dunes that are perhaps taller than they normally would occur or wider than they normally would occur. We actually prevent overwash deposition during those moderate storms that are so important in elevating island level. Also the installation of seawalls, much like the building of tall dunes in the case of that road that I showed in Buxton, also prevent the delivery of overwash. In some cases, when overwash is delivered to these landscapes, when overwash is deposited on roads and in neighborhoods, understandably, we want to get back to those buildings and our homes, and so overwash is removed. And so this this process that's elevating the landscape so that it can be maintained under changing conditions is sort of undone in many cases. And in the case of development, there's another factor, which is that the presence of development, either in the density associated with residential development or density associated with commercial development, has been shown to actually filter overwash and reduce the delivery of overwash to the island interior, therefore limiting the degree to which these processes can be effective in elevating the landscape and maintaining island width to reduce long-term vulnerability. So these overwash and migration processes are important, and they're also incredibly challenging. They pose significant challenges to coastal communities. These actions that are understandably taken that seem necessary for short-term resilience actually are in tension with the long-term maintenance and long-term resilience of the coastal landscape on which communities rely. And so this is one of the central challenges to much of the work of Seacoast and communities at large is how to maintain community resilience and landscape resilience at the same time. So just a quick summary here, and then I'm happy to take questions. Talked about the effects of storms on the landscape and the fact that it's the relationship between the total water level generated by a storm and the elevation of the landscape that determines how storms impact coastal environments. Moderate storms, sand is moved offshore. During intense storms, overwash occurs, and this is where island elevation and width are maintained as sea level rises. Extreme storms cause inundation and then aren't really as effective in building up those elevations. So the intense storms are really important to the maintenance of back barrier, the maintenance of barriers through time. Sea level rise and increased frequency of storms increase overwash frequency and cause these processes to occur more often and are important in the persistence of barrier island landscapes over time. And then coastal management actions that increase short-term resilience are in tension with the long-term resilience of these communities and landscapes on which they rely. And I'll just make the point again that much of what I've shared here, although I've really focused on the barrier island landscape, does apply to low-lying sandy coastlines in general. And with that, I will pass it back to Catherine, who will moderate the Q&A for us.
Okay, thanks for that, Laura. All right, I have a question that came to me through chat. Is swell direction, for example, northeast swell versus southeast swell, or swell height and period, more important to coastal erosion rates during storms?
Well, certainly the direction that waves come from is important, and I'm going to let Brad Murray pick up on that, because in this first part here, I'm really focusing on the cross-shore dimension, and the direction that waves come from is really important in determining along-shore sediment transport processes, which are another mechanism by which erosion takes place. During storms, if we were to think about the effects of storms specifically instead of sort of long-term chronic shoreline erosion, certainly the direction that waves are coming from will influence the direction of the direction alongshore that sand is transported. And if you have a littoral cell, like on the West Coast, we have these compartments that we call littoral cells. And so if waves are coming from the south, they'll tend to push sand to the north. If swells are coming from the north, they'll tend to push sand to the south. And so you can get, in addition to the erosional cycle in the cross-shore dimension, you can see some oscillation of shoreline orientation as a function of wave direction during storms. Brad maybe will touch on that, although I know he's focusing on long-term chronic erosion primarily in the longshore direction.
Okay. Another question. Does overwash removal have consequences for the mainland coast? Or would that
mainland coast?
Yeah, for the mainland coast. Or would that only matter if barrier islands went away entirely?
That's a great question. And the second part of it kind of answers the first part to some degree. I mean, I would say that the main consequence for mainland environments is that the removal of overwash makes islands more vulnerable to inundation. And of course, inundation is that situation in which the island is completely covered in water during storms, and sand is carried from the nearshore environment across the island and lost to the bay. So we're not building islands during those events. And so more vulnerability to inundation leads to the possibility that islands won't be maintained and might drown, become narrower over time, and therefore not provide the protection to the mainland that they currently do. And there are places on the Virginia coast where we're seeing the erosion of the northern and southern ends of islands on either side of an inlet. And there is an increased amount of wave energy and wave erosion experienced on the mainland side of that inlet for the reason that the island is not extending as far into the inlet as it used to. And so it's a very interesting question and an important one to think about, because I think we often consider the challenges that are faced on barrier islands as facing barrier island communities alone. But there are huge implications for those who rely on the bays behind, because the less continuous barrier islands are, the more impactful ocean processes are to bays. You know, bays can become more saline, that can affect fishing, can affect recreation, the distribution of shoals and boating. And then also the mainland communities, if we're seeing barriers be less effective barriers to ocean processes for mainland communities, then that is a reason for mainland communities to also have an interest in what transpires on the barrier islands. These are very challenging questions where there is this central tension, and understandably, you know, how do we achieve coastal resilience is a big question. A lot of challenges in there, of course.
So that kind of leads into another question. Are there any effective mitigation strategies, say based on management of built or natural environments, to reduce the effect of overwash? To reduce the effect of overwash. I'm thinking on developed.
So I'm wondering if, what's that?
Go ahead.
So can you read that one more time?
Sure. Are there any effective mitigation strategies, say based on management of built or natural, or of the built or natural environment, to reduce the effect of overwash? So I'm wondering here if it's for developed systems that they.
Right. So it's interesting because overwash is certainly a challenge and detrimental to a neighborhood, right? If your neighborhood gets a meter of overwash deposition, that's a problem, because then your roads are buried and your driveways buried. From the perspective of the island maintenance and the natural processes that have been occurring over thousands of years and that need to occur if islands are to persist in the future as sea level continues to rise, overwash is a good thing because it makes you less vulnerable. And so that's one of those key places where, yes, you might want to prevent overwash deposition. And if that is the priority, then you could build a tall dune and only have overwash occur during the most extreme storms when it happened, and it might end up being inundation because you're kind of out of equilibrium with the system in terms of your dune height. So that could provide protection from overwash events and prevent overwash from being deposited in your neighborhood or your community. But it's also increasing long-term vulnerability because it means you're not maintaining the elevation and the width necessary to be less vulnerable as conditions change. And in some cases, if we don't maintain island elevation in some way, forget about the front side. There's also the back side of the island to worry about, and sea level's rising there too, right? So in some cases, we can see detrimental effects coming in. I mean, when you don't maintain the elevation of your island, you also become vulnerable to sunny day flooding. That's flooding that's occurring just because your landscape is low relative to sea level. And when it rains, there's nowhere for water to go, or tides just themselves flood parts of the landscape. And so the maintenance of elevation is not only a factor in the persistence of barriers, it also affects vulnerability to other factors that rely on elevation, like sunny day flooding. And so, yeah, maybe I'll leave that one there for time. It's a great question, and it's a challenging one.
So we have two more similar questions. What coastal management actions are not in tension with long-term barrier island resilience?
Is that a question?
Yeah, that's one question. And
wait, but what's the question?
What coastal management actions
are not? I didn't hear the first part.
Yeah, are not in tension with long-term barrier island resilience.
Yeah, and that's a great question.
And the second one is similar. Are there positive feedbacks between humans and barrier island evolution over longer timescales?
Positive feedbacks. Okay, yes. So let me take the first one. You know, what I thought was so interesting about Bolivar, Texas, is that like 1,000 homes were wiped out by Hurricane Ike. We didn't hear a lot about it because it occurred in 2008, just after the stock market crash and just before President Obama was elected to office. So there were a lot of things going on in the news. But 1,000 homes were lost. There were buyouts, there was rebuilding. Now it's a much different community than it was before, which has pros and cons. But the thing I noticed there is that some of the properties were not rebuilt with homes on them. They actually are now occupied by a screen porch on stilts, very high stilts. And what is placed below is a mobile home, a nice mobile home, so that if there's a storm, one could drive away from it. And what's lost if there's a 20-foot storm surge again is a screen porch and some pilings. And so it's a radical change from what we're accustomed to. But really, if we're thinking long-term about these communities and these landscapes and what they need to coexist and remain in place if we want to enjoy them in the future, is a means for both the landscape to be resilient and communities to be resilient. And something like homes that can be moved as the island shifts over decades and centuries could do it. It's a radical change from what we are accustomed to in coastal environments. But I don't know, we could look to Scotland. They have wonderful caravan holiday communities which are revered and delightful, and they're small homes that are potentially mobile. So it would require a paradigm shift, but I think there are ways to adapt and change our coastal communities as they experience the severe effects of storms that could allow us to be there in the longer term and to provide protection to the mainland communities that rely on barrier islands. And the second question I'm now forgetting. I think it was a tougher one.
Yeah, it was what positive feedbacks between humans and.
Yeah, so I'm sure Brad will touch on this again, and maybe I'll throw the ball mostly to him, but a lot of what we're studying these days in our group and other groups, and those on the call here could speak to this as well, Marty, Satya, Dylan, Brad, are the interactions between the decision-making and the natural processes. So a feedback is, for example, shoreline erosion occurs, people respond by putting in a tall dune, or putting in a seawall, that affects the natural processes. It affects the overwash delivery, it affects shoreline change rates. And so that's when we say positive, we mean, I'm interpreting that as self-reinforcing. You might say that's not a good thing. So it's not positive in that it's necessarily good. It's not a judgment about good or bad, but it's a self-reinforcing feedback in that the decisions that are made in response to changes in the natural system affect the natural system. And then the changes in the natural system affect the decisions that are made. And so a lot of research that I hope can assist in achieving a more resilient future has to do with understanding these self-reinforcing feedbacks and the mechanisms that drive them, and allowing us to think about ways that communities might use those feedbacks to their advantage to provide a more resilient system in the future.
Okay.
We must be out of time for
You're
questions.
out of time. I went over. Sorry about that.
Okay.
Sorry, Brad. Okay, Brad, you are on.
All right, I will get my screen shared in a second here. And then I'm going to make controls go away. All right, so I'm going to assume that you can hear and see me unless I hear otherwise. Actually, am I muted?
Oh,
No.
you're good.
Nope. Good deal, because I made that control go away too. Thank you. All right. I'm going to talk about what causes long-term shoreline change. And this includes, I see the controls don't stay gone, but I'm going to try one more time. This includes the cumulative erosion that brings shorelines into contact with development. Development is typically built well back from the shoreline. Using this example from Nags Head, the shoreline, when this area got heavily developed, was probably out, or must have been somewhere around out here. There are regulations that define a setback line and prohibit new construction seaward of that line. And that line is typically for houses a distance equal to 30 times the average annual erosion rate. So the idea is to be far enough away from the shoreline that the houses will last a while. So it's this long-term erosion that brings the shoreline up next to these houses, and in other places the shoreline has moved past rows of houses and even frontal roads in places. So what causes this long-term erosion? Part of the answer is the component of shoreline erosion that's related to sea level rise via overwash that Laura talked about. This is going to become a stronger signal later in the century as sea level rise rates increase. But at least for now, in most locations, the dominant cause for ongoing shoreline erosion, or in some places shoreline accretion, building seaward, is related to gradients in alongshore sediment transport on relatively large scales that I'll talk about. So to start with, this alongshore sediment transport arises in the first place chiefly because, as Laura mentioned, breaking waves push the water in the direction they're moving. This is what causes the wave setup in the cross-shore direction, but there's also an alongshore component of this force in the zone where the waves are breaking. The alongshore component of this force can actually generate a current. And by the way, this schematic plan view has got a really exaggerated angle for these breaking waves just for illustration purposes. On most days, the wave crests look much closer to parallel to the shoreline, but you can still have this, you still will, unless those wave crests are exactly parallel to the shoreline, which happens vanishingly often. There will be some alongshore component to that force, which generates this alongshore current right in that zone of breaking waves and a little farther offshore. Now, this current is usually so subtle that it by itself wouldn't carry any sediment, wouldn't entrain any sediment off the bed, but breaking waves generate a lot of turbulence. And this turbulence can stir up the sediment, which can then be passively carried along with this subtle current. And over time, since this is always happening, over time it adds up to a lot of sediment moving from one place to another along the coastline. Some days the waves are approaching from the left and the longshore transport is moving to the right. On some days, the waves are coming from the right and the transport's going to the left, as Laura was mentioning. But if we add up the amount of sediment passing a certain point on any coastline, there's typically a pretty good net transport when you add up what's going to the right and what's going to the left, and their net effect is typically a lot of sand moving along the coastline. And so it's kind of like, it has the same effect as a stream of dump trucks marching down the coastline, and we'll use the terminology of downdrift for this, the direction of net alongshore transport. And averaged over time scales of a year, it might be typically something like a couple of dump trucks a day passing any given point on the coastline. Now, the next point is a key one here, that really it doesn't matter very much how much sand, how much sediment is moving past a given point on the coastline. What matters is how the amount of alongshore sediment transport varies as you move along a coastline. So this is showing a situation where we've got a gradient in this net alongshore sediment transport. This applies over the time scale of something like a year and longer. That in this case, we have a gradient where there's a decrease in the transport as we move along the shoreline. So if anywhere in this zone, we draw an imaginary box, we've got more sediment coming in one side than going out the other over the course of a year or 5 years. So if in the long term, we're gaining sand in this imaginary box, then the shoreline must be building seaward, must be an accreting shoreline. It's the yellow arrow. On the other hand, if we have the opposite sort of gradient, a divergence in this alongshore transport, so that as you move along the coastline, the net transport increases, so there's more sediment leaving the box than entering it on the other side, then over the long term, if we're losing sediment, the shoreline must be moving landward. Now, next point is more of a minor one, but it doesn't really matter what the magnitude of the transport is. What really matters is this gradient, how fast the net transport changes as you move along the coastline. So just to toggle back and forth here, in the previous slide I showed longer arrows. This would be either a coastline with bigger waves or waves more consistently coming from the left. And here the waves, the arrows are smaller, so there's less net sediment transport, but the gradient is about the same, and the erosion rate wouldn't know the difference between those two. And so this just gets to the point that it's often thought that bigger waves mean more erosion. Bigger waves tend to mean more transport, so that the magnitude of the net transport would tend to be bigger as the wave heights got bigger, or as the wave climate featured more bigger waves, but that doesn't necessarily equate to more erosion. It could even be accretion that happens more rapidly because the wave heights are bigger. Okay, so it is these gradients in net alongshore transport that cause the long-term shoreline change that can bring the shoreline back into the proximity of communities and structures. And this is just to reinforce the points that Laura was making earlier, that the cycles of storm erosion and recovery that we get on time scales of weeks to months don't directly accomplish this long-term shoreline change. The storm erosion and recovery cycles basically amount to wiggles in the coastline position over long time scales, over time scales of years to decades. It's just the coastline, the shoreline wiggling back and forth within some envelope. And as long as that envelope doesn't get too close to the structures, that doesn't directly affect the structures. It's when the long-term erosion brings the shoreline and this envelope of wiggling shoreline positions so that the structures start to be within the envelope of shoreline positions, then storm-related erosion becomes a big deal, and houses get knocked down, and et cetera. So but that's not directly tied to the long-term erosion that causes the shoreline and the houses to be in close proximity. Okay, yes. Okay, next step is, so where do these gradients come from? And there are various answers to that that for time's sake, I'm going to focus on subtle shoreline curvatures, a shoreline shape that is highly exaggerated in this schematic plan view here, just for illustration purposes. Imagine that this is really a slight bump in the coastline that you wouldn't even notice looking out there, unless you looked very closely or were up in an airplane taking an oblique air photo perhaps. But it doesn't take very much of a curvature in the coastline to actually give you a gradient in a longshore transport that can cause a very noticeable erosion or accretion in some places. And the way I've drawn it here along this part of the coastline, we've got an increase in the net alongshore transport. And the reason this arises is just that different shoreline orientations experience somewhat different interactions with the wave climate. So I think intuitively it makes some sense that we would have different amounts of transport on different coastline orientations. And as you move along the shoreline and the orientation is changing, i.e. if there's curvature, then the net transport's going to be changing. And I'll not go into the details beyond that, but I'll point out that the way I've drawn these gradients here, we have erosion going on along this subtle bump in the coastline, and accretion, or perhaps it's reduced erosion if this is an otherwise eroding coastline. Over here where the curvature is concave seaward, we tend to have accretion. Now, big caveat here, this smoothing of coastline shape doesn't apply in all cases, and there are important cases, situations where really interesting and important interactions happen because of the opposite kind of behavior, where the coastline, instead of getting smoothed, is getting roughened over time. But for the purposes we're talking about here, in most places along coastlines, over spatial scales up to several tens of kilometers, this smoothing tendency is a really good assumption. And so what we tend to have is, if we just made a bump and let the alongshore sediment transport do what it does, then that bump would be spread out. So we tend to get erosion around the crest, and this reduced erosion, if it's an overall an eroding shoreline, on the flanks. And this effect on the flanks of this bump is completely symmetric for subtle bumps. This is perhaps a little counterintuitive, since we've got a net direction of transport here that, left is not the same as right as far as the net sediment transport goes, but the effect of the smoothing of the bump is symmetric, and that'll come into play when we talk about stabilization shortly. Okay, then the next level of question is, what causes these curvatures in the shoreline, in the coastline? And there are a bunch of answers to this. I won't go into the details of any of them, but the opening and closing of tidal inlets and associated sediment sinks and sediment sources cause curvatures in the coastline to develop. The alongshore variations in the kind of material that's underneath the coastline and the nearshore seabed can cause curvatures in the coastline to develop that then interact with the wave climate and this smoothing tendency. Another way to get coastline curvature that I'll focus on here is shoreline stabilization. So in the easiest instance to think about, imagine that this is shoreline stabilization through beach nourishment. So this community has gone through a cycle of beach nourishment where they widened the beach out in front of their community to undo some of the erosion, or all of the erosion that had happened in the last handful of years. So that addition of beach width itself creates a subtle bump in the coastline, and this bump will tend to be smoothed out over a few years, something like a few years. But if we think longer term than that, if this community continues to stabilize their coastline through nourishment, so they nourish every so often to keep, in the long term, they're keeping the shoreline position fixed in their community with some wiggles representing different parts of the nourishment cycle. But in the long term, if the shoreline in front of the community stays fixed, but the shoreline in areas away from there continue to erode, we're assuming this is an eroding coastline or wouldn't be doing the stabilization, then we've got a bump in the coastline that gets more exaggerated the longer you wait. And as this bump gets more exaggerated, the longer you wait and the farther the other parts of the coastline recede, then the curvatures are getting larger over time, progressively larger. Larger curvatures mean larger gradients in transport. That means faster erosion and more pronounced accretion, or a tendency to accrete, which on an eroding coast is probably just reduced erosion. And so this community is going to have to expend their resources to stabilize the beach faster and faster as time goes on here. And this affects the coastline much farther than we might normally think. When we think about timescale of decades instead of years, then these effects can extend for tens of kilometers along the coastline, reducing the erosion rate. And this brings up all sorts of implications that, well, one quick digression, when we're trying to measure long-term erosion on much of the East Coast, we find that we can't do it anymore by looking at the coastline at one time and looking at the coastline at another time, separated by a bunch of years, and just a little more sophisticated than that, but that kind of approach to finding the erosion rate of a coastline, it doesn't work anymore because there are enough communities nourishing in enough places that effectively those communities that are nourishing are stabilizing large stretches of the coastline. And they're actually affecting other communities along the coastline as well, but they're doing enough stabilization of the large scale coastline that they are undoing the erosion that is always tending to happen. Those coastlines are still tending to erode, of course, and so they're still eroding coastlines in a real way. It's just that we can't see the coastline changing over long time scales anymore. Okay, so humans are doing this stabilization in response to shoreline change, but shoreline change is responding to what the humans are doing just as much as humans are responding to shoreline change. So there's a tight coupling going on in here clearly. And if other communities are nearby on this coastline that is schematically depicted here, their erosion rates are going to be affected by this community's stabilization efforts. Now, it's not always as simple as it's drawn here, where basically we're reducing the erosion everywhere along the coastline, and the longer we wait, the farther that the appreciable effect spreads. It can be more complicated on more complicated coastline shapes, where the effect of stabilizing one part of the coastline isn't as simple as this, but on these spatial scales of some tens of kilometers, this is a good place to start to think about it for sure. So if there's other communities nearby, this is just some simple model results where we have two communities as a longshore position, and we can vary the distance between these two communities that are both stabilizing through beach nourishment, showing the shape of the coastline over time. And this is showing that the closer the towns are to each other, the less rapidly they have to expend resources to stabilize their shoreline. Details not greatly important here, but this brings up the point that this stabilization is really expensive. Not every community can afford to do it that would like to have their shoreline stabilized through beach nourishment. And this is showing one example of an approach to calculating the stream of benefits that you get from shoreline stabilization through nourishment. And this is developed by Marty Smith and Satya Gopalakrishnan, and probably will see something that looks something like this in 2 weeks when they talk and teach us some of their discipline. So you can calculate the benefits of stabilization, compare it to these very high costs, and economic analysis sure comes to mind when you're looking at something very expensive and balancing costs and benefits, and that there's a lot we can learn from that kind of analysis of the human component to this system. But of course, there's other social science disciplines that have somewhat different lenses or considerably different lenses on this same human component to this same coastal system. So that's part of what we hope the Disciplines 101 sessions will do, is to have a lot of us learning each other's varied perspectives. So to summarize over some of the key points for both Laura's part of this and for mine, decision making has become an integral part of coastline systems, of coastal systems over these last handful of decades that we've had these heavily developed coastlines and the pattern of coastal stabilization and defenses against storm impacts, etc. So clearly there's a strong coupling between human and natural dynamics. So we can just start with the fact that the storm risks and storm impacts, as Laura described, are functions of the elevation and width of the landform, of a barrier landform. But over the time scale of years to decades, the height and width of the landform and therefore the storm risks and impacts are a function of the decisions that have been made over that time, over these years and decades. And those decisions are, of course, functions of the impacts and risks that are occurring. So you can't, and similarly for shoreline erosion, it's the decisions we make are affecting patterns of shoreline erosion, but the patterns of shoreline erosion are what drive the decisions as well. So it's clear here that we can't address how the human component of the system might evolve into the future without thinking about the risks and impacts and chronic stressors like sea level rise and shoreline erosion. But we can't also try to understand how the evolution of the physical part of the system and the exposure to storm processes will change without addressing the human component of the system. So this really is a new system that's not been around for that many decades. New dynamics emerging within this system, a lot of it having to do with the coupling between human and natural processes. And we don't know very much about this system at all yet. And hopefully over the next couple of years, with trying to teach each other our different disciplinary lenses, we can make a good start on that. So I'll finish by saying we will get a reading list posted later today. And for now, just see if anybody has any questions or points they'd like to bring up.
All right, we have lots of questions. First question. What methods or analyses are currently being used to make decisions in coupled human natural systems?
I tempted to ask a question back. So there's the way that can you read the question again? Let me do my best.
Sure. What methods or analyses are currently being used to make decisions in coupled human natural systems?
So I'm going to take this to be in models of coupled human natural dynamics, because I don't think that I'm qualified to say what all the different ways that decisions are actually made in the coupled system. But in the modeling that's been done so far, the decisions are driven by economic calculations. A lot of the work that I know of that some of us have done together, it's that trying to optimize the net benefits of stabilization, if stabilization makes sense economically for a community based on their property values and the erosion rates. how often should you nourish to get the most economic bang for the buck? And that drives a lot of the coupled dynamics in work that we've done over some years, and comparisons to observed nourishment intervals suggest that there's a lot of that kind of an economic approach captures a lot of the net effects of the human decision making. Clearly, people aren't explicitly making those calculations, but in mass, it seems that people behave as if they were making those calculations. That being said, there's a lot of politics and sociology and psychology that goes into people making the decisions they do, and that's part of what we hope to address in the coming years here together. So that question I will put aside to some great degree. There are agent-based approaches to decision-making too that have a lot of economics as well as empirical bases for agents' preferences and sensitivities to risks and things like that. That work is under development and coming along, but that's an alternative approach as well.
Okay. Is shoreline stabilization and the resulting bump an example of a positive feedback, like what was asked in the first talk?
Yes, so positive feedback, self-reinforcing, it can be. In the simple physical sense that I was showing, no, that's a negative. That overall, the shoreline system, if you're in the kind of situation where gradients in a longshore transport tend to smooth out the coastline, that is, from the physical point of view, a negative feedback. If you start with a smooth coastline, it's stable. And if you perturb it a little bit by making a bump, it comes back to where it started. So that's a negative feedback, and not in the good or bad sense, but in the self-reinforcing or self-undoing sense. Once you get the human dynamics in there, yes, there are great potentials, and there's some work that shows that supports the hypothesis that once you start stabilizing a coastline, that encourages more and bigger development, because it seems like well, economically it makes sense given that kind of analysis that I just hinted at, and there's a sense that it's maybe a safer environment because it's being defended and nourished, and maybe dunes are being maintained nice and large, and it might be a mislead from the long-term point of view, that might be a misleading impression, but there certainly seems to be the impression that protection makes it safer, which begets more development, which begets more protection, which begets more development. So in the coupled human part of it, I think there is a positive feedback, not in the good and bad sense, but in the self-reinforcing sense that is at least potential.
Okay, so what about hard stabilization instead of management?
Yes, great question. Some of the things that I talked about apply also to hard stabilization. And in the reading list, there'll be a paper that contrasts and compares the effects of stabilization, and we're talking purely for combating erosion here, for preventing long-term erosion, doing it through either beach nourishment or hard structures. When you think about the decadal scale timescales, those two ways of stabilizing the coastline have some things in common and some big contrasts. And one big contrast is to do it through nourishment, you're adding sand to the system. So you can have a symmetric sort of, from the human point of view, a benefit that goes up drift and down drift. To do it through structures, you're not adding sand. So even if you arrest the coastline position at one spot on the coastline, you might be benefiting the updrift coastline, but you're having basically a symmetrical increase in the erosion tendency on the downdrift side. So the big difference is whether you're adding sand and you can sort of combat erosion, effectively nourish whole chunks of coastline both directions, or whether you're just pinning the coastline in place but not adding sand. So there are significant differences for sure.
Okay.
I might add there too, if you don't mind, Brad, that if we think about the cross shore, what we could depict in the cross shore, that there's quite a difference too, in that when we're adding sand to the system, we're sort of offsetting that removal of sediment during overwash from the beach and the dune environment that gets placed on the top, which is a component of long-term erosion associated with sea level rise. We're replacing that with sand into the system. Whereas with a seawall, it's more like sort of that road example potentially, or we're preventing the transfer of sediment to the interior as well. So there's a cross-shore difference that comes into play there too.
Yeah, for sure.
It's also involved in feedbacks.
Good point.
Okay, this is a long question. I think it will be our last question. It's related to North Carolina. So if it is the slight curvature that leads to shoreline erosion many coasts are experiencing, why doesn't that work itself out through time, ultimately creating a straight shoreline? ...
Thank you.
Problem solved. Wait, there's more.
Okay.
Something like 70 to 80% of the North Carolina oceanfront is eroding. How do you bring these two observations and signals together?
Beautiful question. Thank you so much. I had meant to refer to this in the talk, so thank you for reminding me. So, two-part question. One is that some of the influences that generate this curvature don't go away. If we just made a bump in a coastline in an area where the waves were, the alongshore transport gradients are tending to smooth out the coastline, the bump would go away. And then the first part of the question is really good. Why do we still have any bumps around? But the factors that generate these subtle curvatures in the first place, like alongshore heterogeneities in the underlying geology, the underlying material that the seabed is eroding into, those continue to generate curvature as the coastline erodes. So that doesn't go away. And that the opening of inlets and closing of inlets generates curvature that keeps, getting redone here and there, as inlets are very dynamic. Now, the key point here, so much of the coastline is eroding. What's up with that? Two-part answer. One has to do with, well, the sediment sinks. So opening of inlets tend to take a lot of sediment back into the back barrier environment and basically sequester it there. It's not lost forever, but it's taken away from the nearshore environment, and that tends to have erosion influence that spreads via the curvature of the coastline along the coastline nearby, as long as those inlets are growing. So that's a key, that the sediment sinks. The big shoals off North Carolina act as sediment sinks as well off of the capes. Each of those capes are basically the sand that's moving along the coastline on the northern flanks of the capes is being sequestered in these shoals, which act as sinks. That's a huge factor. That brings me into, so sediment sinks is part of the answer. The other part of the answer is large scale shoreline shape, which I didn't touch on. But the fact that the North Carolina coast as a whole on large scales has this really well-developed pattern of shoals or of capes and bays in between. It's related to patterns of alongshore sediment transport and gradients, just the way I've described, with the additional interaction of wave shadowing effects that I don't have time to go into, but the short version of it is that these big capes, they're kind of like bed forms, like ripples or dunes on their side, and they tend to migrate along in the direction of net transport. So the updrift flanks of these capes are always going to be erosional. It's gradients in alongshore transport related to the large scale structure, these big emergent structures, and the behavior of those big emergent structures. So we can, on these scales of tens of kilometers where communities might be interacting with each other, it's a decent approximation to think of it as just an eroding coastline with some subtle curvatures superimposed on it related to stabilization or not.
Okay, loaded question, loaded answer. We are out of time. Thank you all for coming today. This recording will be on our website. And thanks for all the good questions. We'll see you in 2 weeks. Bye, everyone.
Thank you all.
Thank you, Catherine. Thank you all.
Bye, everybody.